Hello everyone, and welcome to today's chem lesson. Today we are going to be spending some time talking about the more mathematical aspects of heating and cooling. When we look at a phase change, as we said in our previous video, we know that certain changes require energy to be put in, certain changes require energy to be put out. Right? We need to cool down a gas to make it become a liquid. We need to remove energy from that. You need to put energy into a solid to make it become a liquid. What we're going to focus on today is how much energy do you need to put in? How can we calculate how much energy needs to be put in? How much energy do I need to increase the temperature of something or to change its phase? And that's where this beautiful diagram comes in. This on the screen here right now is a heating curve. The nice thing about a heating curve is no matter what substance it is, right? Notice nowhere on here does it say what substance this corresponds to. Right? And that's because every heating curve takes the same shape. It's always three slants separated by two plateaus. Your pattern will always be slant, plateau, slant, plateau, slant, no matter what substance you have. The length of these line segments, the angle of these slants might change, but it will always take this shape. And so when we say anything about this particular heating curve, we are talking about every possible heating curve. Let's talk about these axes. Right here, as we move along the x-axis, we see time in minutes. Right? As we move from left to right here, we're going further and further along in time. As we look along the y-axis, we're increasing temperature from low temperature to high temperature at the top. When we look at this shape, we see that there are a distinct 5 segments, right? The 3 slants, the 2 plateaus. And so what we're going to do is actually label each one of these. I'm going to change font colors a couple of times here. Here we have the coldest thing we're going to get. If you think about it, the phase of matter that is the coldest is going to be a solid. This line segment AB is going to represent the solid phase of whatever substance you're talking about. If we think about what could go on the other slants then, liquid and gas are pretty easy to fill in. But that leaves us with 2 plateaus, 2 flat spots, where we're going from a very hot solid to a very cold liquid, or a very hot liquid to a very cold gas. These transitions are going to be our phase changes, right? How do we get from solid to liquid? Melting. How do we get from liquid to gas? Boiling. So now we've at least labeled all 5 of our pieces. As you heat something up over time, it starts as a solid, it gets hotter and hotter and hotter. It melts, becomes a liquid, gets hotter and hotter and hotter. It boils, becomes a gas, gets hotter and hotter and hotter. That pattern is true of every substance. There's nothing that is a gas first and then becomes a liquid later. Right? It starts with temperature as at lowest at a solid. As you heat it up, it becomes a liquid. As you heat it up, it becomes a gas. Now, I want to take a second. What is happening on these plateaus, on these flat bits? You have something that was heated up. Now we have a flat piece here. What does this flat piece signify? We're still going forward in time, right? We're not talking about time stopping. Right? Time is going to continue to march on, as it always will. So this flat piece here represents the fact that the temperature is remaining constant. So we have a phase change. This is also true of our boiling, right, from line D to E. So during a phase change, temperature is constant. That's my first observation here. But now let's think back to some of the stuff we talked about in our previous video. We talked about how temperature is another word for average kinetic energy. So we can say that the temperature is constant. We could also say that the kinetic energy is constant. But when you're melting or boiling something, you don't turn off the flame once you reach that point. You continue to heat it up. You continue to apply heat to it. If that heat energy is not increasing the kinetic energy, it must be increasing some potential energy. So as we go through a phase change, we're not changing the kinetic energy, we're not changing the temperature. Any energy that we are adding is going to be in the form of potential energy. And if that's true of the flat parts, the opposite must be true of our slanted parts. We can summarize this by saying on a plateau, kinetic energy is constant. Potential energy increases. And then we can say on a slanted part, kinetic energy increases while potential energy is constant. And that is well and good, but I did promise that we were going to look at some of the math aspects of heating and cooling curves, and there are no numbers on this page right now. So let's talk about the actual mathematical aspect. If I want to know how much energy it takes to melt a thing, I have a formula that I could use to calculate that. If I want to know how much energy it takes to heat up a liquid from temperature A to temperature B, I have a formula that can calculate that. Each line segment, right, from A to B, from B to C, from C to D, from D to E, and from E to F, has its own formula that can be used along the segment. The really nice thing is that these formulas are the same for every slant and are the same or are very similar for each plateau. So for the slants, we're going to see the same formula used every time. Q equals MC delta T. And on the plateaus, on the flat parts, we're going to see very similar formulas to each other. Q equals MHF and Q equals MHV. Now, we're going to come back to this heating and cooling curve in a second, but let's take a swift detour to talk through these formulas. Here we have our wonderful three formulas, right? Q equals MC delta T is used for calculating the heat needed to increase the temperature of a substance, and like I said, it is on the slants. Q equals mhf is used for calculating heat needed to go from solid to liquid. So the first plateau, hf, which really stands for fusion, but if you think of it as F for first, you're never going to mess that up. Q equals mhv is for going from liquid to gas or gas to liquid. And V goes really nicely for vacant, which isn't a word, but if you remember it as vapor, right, having to do with gas, you will always get that one correct. Now, all three of these formulas are available for you to find on Table T of the reference table. They're all listed there, and on top of just listing them out, it also identifies what each variable stands for. All right, we've got 6 different variables here. First is Q, which is going to be heat energy. Right? How much energy does it take to do thing X or thing Y or thing Z? That's what Q is going to tell you. It's going to be how much energy. M, trustworthy. M is always going to be mass for us, right? So it's how much of the substance are you trying to change the temperature of, or how much of the substance are you trying to melt, or how much of the substance are you trying to boil. C is something called specific heat, which is a measure of how much energy you need to increase 1 gram by 1 degree Celsius. Right, if I want to take this single gram block of ice from the -4 to -3, that would be my specific heat value, right? 1 gram and increase it by 1 degree Celsius. Specific heat is different for every substance. Substances that are easy to heat up, things like metal, have a low specific heat. They absorb energy really easily. They are good conductors of heat. On the other hand, something with a high specific heat value is something that is difficult to heat up. That would be something like a piece of wood. Right? Wood has a very high specific heat. It's hard to just make a piece of wood hotter than it is. Now, that's not burning it, right? But just heating it up and making the piece of wood hotter. Right? This is why we use wood spoons and wood utensils, but metal pots and pans. Then we've got delta T. Delta T is not 2 separate things. Delta T is one variable that is used to say the change in temperature. The delta can go in front of pretty much anything, right? You can say delta M to talk about change in mass. You can say delta V to talk about change in volume. Delta P, change in pressure. Right? The delta is always just going to mean change. So when we talk about delta T, we're talking about one thing, and it's what is the change in temperature. Down here, our HF and our HV, those are heat of fusion and heat of vaporization. Similar to specific heat, these are values that tell you how much energy you need to melt 1 gram of the substance or boil 1 gram of the substance. C, which I'm going to now outline in green here, HF and HV are always going to be the thing you solve for, or something that is given to you. The only time that is not true is when we're talking about water, in which case we have table B. Table B gives you heat of fusion, HF, heat of vaporization, HV, and specific heat, C, for water. So you can always look up those values and pull them in when you need to. Every other substance is either going to be given to you in the text of the problem, or it will be the thing you are solving for. So if we go back to our heating curve now, we can see each of the formulas in their place. It makes sense now if we think about delta T, right? It's only on line segments where the temperature is changing, right? If you tried to put delta T into one of our plateaus, it would equal to 0, making the whole thing equal to 0 every time, no matter what. And so delta T is only going to occur when we're heating up or cooling down a solid, a liquid, or a gas. When you're doing a phase change, there is no change in temperature. I have some practice problems for us to look at, some practice problems for us to do relating to our heating and cooling curve. So here we have 3 problems. Now I would like you to take your time, take about a minute per problem to do your best to solve it out. Pause the video if you need more time, but I'm going to wait about a minute, maybe a minute 15, and then jump into solving these one at a time. And again, remember, you can pause the video. That is an option that you have to enable you to use more time. Okay, let's take a look at question number 1. Here they're asking us how much energy is needed to increase the temperature of 50 grams of water by 30 degrees Celsius. The fact that we're changing the temperature means that we are operating on one of our slants. Further reading of the question reminds us that this is liquid water, and so we are going to be operating on slant CD. The formula that gets used on slant CD is Q equals MC delta T. And so that is what we are going to plug into as we try to solve this problem. They're asking us how much energy is needed, which means we're looking for Q. We're going to try to solve for Q. They give us 50 grams. They don't give us a specific heat, so I'm going to leave that for now. I have a pretty good idea of where to go find that. And they tell me that the change of temperature, I'm increasing by 30 degrees Celsius. Now here right now I have two variables. I'm looking for Q and I'm looking for C. And that's not the way math works. I should only be looking for one variable. C, specific heat of water, is given to me on the reference table. Specific heat capacity of water is 4.18 joules per gram degree Kelvin, or joules per gram degree Celsius. 1 Kelvin and 1 Celsius are the same size, so they are interchangeable in terms of change. So I'm going to go 4.18 joule per gram Kelvin. Now I've got three things, one variable. I'm going to just plug in and solve. This is going to give me 6,270. But I need to now determine what unit goes here. I've got grams times joules per gram Kelvin times degrees Celsius. Grams is going to cancel out, right? One in the numerator, one in the denominator. I said before that a change of 10 Kelvin is the same as a change of 10 Celsius. So we can change one of these to match the other. And then they cancel out, leaving me with joules over 1 times 1. The ones are just going to be inconsequential here, leaving me with joules as the unit I pick. For question 2. How much energy is needed to melt 400 grams of copper if the heat of fusion is 0.5 joules per gram? Here immediately I know I am on line segment BC. And I know the formula there is Q equals MHF. They're asking again how much energy is needed, so that'll be a Q that I'm looking for. Mass is 400 grams given to us in the problem. Heat of fusion, again, given to us in the problem. Remember, if it is not given to you in the problem, it's either the thing you're solving for or water, in which case it's on table B. Solving this one out, I'm going to get 200. My units, grams times joules per gram. Grams are going to cancel out, leaving me again with joules as the appropriate unit. My third question here. How much energy is needed to change the temperature of 50 grams of iron from 10 to 80 degrees Celsius? Specific heat of iron is 2 joules per gram degree Celsius. They don't mention it explicitly, but iron, we can assume, is a solid, right? They would have said liquid iron or gaseous iron if they meant anything else. So we know we're solving Q equals MC delta T. They're asking us for energy again. So we're looking for Q given a mass, given a specific heat, given a start and a finish, allowing us to find a change in temperature, right? From 10 to 80 is a change of 70. We plug this in and solve. We're going to get 7,000. And our unit math is going to be the same as it was in our first problem. Where grams and degrees Celsius cancels out, leaving us with joules as our answer. to wrap up our lesson today, I have one multiple choice problem for you. The heat of fusion of a substance is the energy measured during a phase, temperature, chemical, or pressure change. Here, heat of fusion, HF, is something that we're looking at when we are on the first plateau, which is melting. Melting corresponds to which of these following choices? Phase change. There is no temperature change during a phase change. There is no chemical change occurring during a phase change, right? Chemical changes are chemical reactions. All of these things, melting, boiling, freezing, those are all physical changes. And pressure has nothing to do with anything yet. With that, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.